Welcome to my second video on PyTorch. Today we're going to be training a very simple neural network model, and we're going to look at the theory of constructing and training such models. If you really want to be effective at machine learning and be able to do novel things for your research, I suggest subscribing to this channel. We'll be improving our abilities to construct and train complicated neural network models. Watch this video, code along, and I'm sure you'll become a much better coder in the process. Be sure to like and subscribe and enjoy. So the packages we have today are Torch, of course, PyTorch, the tutorial at hand. We have a few functions from PyTorch here as well, and then NumPy matplotlib, and I actually don't need time here. So I'll start by sort of introducing the general idea behind machine learning. And essentially machine learning is sort of like curve fitting data points. And I have a video on that on my channel, and it's probably good to review what exactly curve fitting is in a basic way before getting into machine learning. But it can sort of be talked about as follows. Suppose you have data that consists of an independent vector, not variable vector, it contains multiple things here, and a dependent vector. I'll describe what those mean shortly. So the independent vector I'll call xi. So you can have multiple things in that vector and multiple things in the output as well. And I is the ith value in the data set. So let's actually look at some examples of what that means. So maybe you have xi is the height of the ith person. You have n people, 100 people, and I just gives you the index of what person you're talking about. And yi is their weight, right? So you plot x versus y, you have height versus weight, and height is probably a pretty good predictor of how much someone weighs. So you could probably fit maybe a linear model to that in a simple curve fitting example, and that would be done. It gets a little more complicated though. Well, xi could be a picture. So xi is now maybe a 256 by 256 image on your computer. So xi contains many things. That's why I'm calling it a vector, because a vector is sort of like it contains many, many numbers. So xi is a picture, and yi is the actual digit itself. Maybe it's like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have a picture and you have a label for that picture. And so xi, remember, I would be like the ith picture, and maybe you're 100 pictures. Yi would be the corresponding label for that picture. And then there's my research. It's similar. Well, xi could be a CT scan. So again, xi contains many, numbers. It's all the pixel values of the scan. And the yi are the corresponding pixels. So yi is also a picture where it's 0 everywhere except particular locations where it's equal to 1. And those would be the pixels corresponding to tumors. And that's my research, is sort of like segmentation of CT or PET or SPECT scans that tell you where things are. And so the goal of the neural network is to say, well, I'm going to create a function f. It's very simple. It's just a function. It's simple in practice. It's very complicated to do, but it's a function that depends on some parameters a, and a are all the knobs that you adjust. That's the whole machine learning game here. But you define a function that depends on some parameters, and you make predictions yi hat. So these are sort of like predictions of, the weight, the digit, the corresponding pixels, and it takes in your value here. So it takes in your CT scan, it could take in the height, it could take in the picture of the handwritten digit, and you get a prediction of what your outcome should be. And what you want to do, of course, is you want to make your predictions, which I call yi hat, and the true values, which I call yi, as close as possible. And the way to do that, well, if you define your structure of your function f, xi, and then a, you do this by modifying the parameters a. And so this is where machine learning becomes a little bit of an art, because you get to decide the structure of your function. I mean, maybe the function is just ax squared or x to the a or whatever. That's a very simple function, but a neural network, that function is very complicated. You have convolutional neural networks, fully connected layers, all sorts of things. Your function is arbitrarily complicated. That's sort of the idea behind machine learning. And you get millions and billions of parameters a. A is like a vector of many, many different parameters. What you want to do is you want to modify those parameters a so that yi and yi hat are similar. And, for numbers, that's pretty simple. It's like the numerical values are as close as possible. If you're predicting weight, you want the weights to be as close together as possible as numbers. But, if you're predicting corresponding pixels of tumors and you have actual locations, it's not as simple as just number versus another number, how close those numbers are. You got to be clever about how you define similarity of predictions versus true values. That's where you would define a loss function. I call it L of y and y hat. So it takes in y and y hat And the smaller that this value is, L, the smaller that L is, the closer that those two things are together. It's an arbitrary sort of abstract function right now, but you need to design it so that the smaller it is, the closer the predictions are. So for example, 1, and that's the height and the weight of the person, it's simple because the output is just a number. So if you want the heights, you could take a whole bunch of heights here of people and you collect a whole bunch of weights. Your loss function to make the predictions as similar as possible could be, well, the sum of the squared errors, the difference between these. And if yi and yi hat are equal for all the things, if the model makes a perfect prediction of the weight of someone given their height, the loss value is 0. And it only gets worse. The farther away the values are, well, the worse the model is, the larger this loss function is. So that's sort of the basic idea behind machine learning. You could think of it very, similarly to curve fitting. So let's get into a basic example of training a very simple neural network. So here I'm making some data x and y. These are my sort of independent variable and dependent variable. And I can look at x and y, and I want to be very precise about what these mean. I have not ran this cell yet. I'm opening up a bunch of things. Okay, x and y, like this. And so here I have 4 different things, right? There are 4 different data points. This is my first data point, x, my independent variable, and my dependent variable. My second independent variable, second dependent variable. Third and fourth. So they match up. So what I've done is I've recorded 2 sort of things, and I want to use these 2 things to predict this here. Then I use these 2 things to predict this here. So there's a pattern that is like totally unknown to us. Like, how do you get 1 from 6 and 2, 5 from 5 and 2, 2 from 1 and 3, and 5 from 7 and 6? You could ask someone to come up with some sort of algorithm that takes in these 2 numbers and predicts this. What we're going to do is we're going to use a neural network. And so it's going to come up with some sort of mathematical structure that's going to take these 2 values and predict this here. So the notation I gave above, it means that x, I have all the different xi's and yi's. Well, x1 is 6, 2, x2 is 5, 2, and so on and so on. y1 is 1, y2 is 5. So our data set has 4 data points to it, and we're going to come up with a model that takes in x and should predict y as close as possible. So in order to do this, we're going to take motivation by the sort of heart of machine learning, I would call it, and that's to have as many parameters A as possible. I mean, for most modeling problems, if you're doing a curve fit, you might have 2, 3, 4, 5 parameters. This is a pretty basic problem. I mean, we only have 4 data points and 4 values, but we're going to use a model that has 24 parameters. So it's already too much for most curve fitting models. But with machine learning, this is nothing. This is easy. So the idea is going to be as follows. We'll take each element of x, so 6, 2, 5, 2, 1, 3. Remember, each element would be like 6, 2 corresponds to a single element. And we're going to multiply it by an 8 by 2 matrix. So if I multiply this by an 8 by 2 matrix, this will become, it will go from a vector that's 2-dimensional to a vector that's 8-dimensional. So that's the first step. So we've already increased the dimensionality of our problem. So we've gone from 6, 2 to 8 values. And then what we're going to do is we're going to multiply the next thing by a 1 by 8 matrix. And so each of these matrices, this has 16 parameters, this has 8 parameters. So here we're going to define the matrix. There's a way to do this in Torch that is such that you construct a neural network properly. These are the layers, the so-called layers of the neural network. So in a neural network, this would be like the first layer and this would be the second layer. So here I create my first matrix. The important thing too is when I create these, they're initially created with random values. And that's important for machine learning. When you initialize your parameters A, they're initially random. There's lots of different ways to randomize those parameters. That's a little bit more advanced than what I want to get into right now. But they're initially randomized. So here I create my first matrix. And the way you specify it is really simple, because this is done all the time, this matrix multiplication thing we're doing. What this means is it's going to take in a vector that's 2-dimensional and it's going to return an 8-dimensional vector. So it's automatically going to construct this matrix. And bias is false, meaning that I'm not taking like ax plus b. You know how you have a matrix A times a vector x plus b. It means that b is equal to 0. I'm only doing this matrix operation. So that's why I have bias is equal to false here. And here's my matrix. It says it takes in 2 input features. So you can think of 6 and 2 of 2 different features of our independent data point. And it outputs 8 features. 8 is just sort of arbitrary. I just sort of decided that as a number. It could be 9, it could be 10. You can make your model a little more complicated. But here I'm going to stick with 8. And so here's M1. So what it does is if I pass in my vector x, which is the data set, so this x means like all these points here, what it's going to do is it's going to take each element xi, which is called an instance in machine learning, which is a 2D vector, and m is going to apply the same matrix multiplication to each element xi. So it's going to multiply this by the same matrix as this, by the same matrix as this, by the same matrix as that. So it's the same matrix being applied to all of them. So I can call m1 of x. Remember, x is just this tensor here, which I defined. M1 is this, which I defined here. So M1 of x. And I have four things. Like, remember, I had four independent variables. But each of these 2D vectors is now an 8-dimensional vector. What I then do is I chain it with the second matrix, M2. So this is another thing, but it takes an 8 input thing. So this is an 8-dimensional vector. It takes an 8, and it will return 1. So this is my second matrix, like this. It takes an 8 input features, 1 output feature. And so I can chain these together. Well, M1 of x will return this. And then what M2 will do is it will say, okay, there's 8 different things per instance. And I'm going to go from 8 to 1. And if I chain these together as an operation, I now get sort of a single value returned for each thing here. And this might be a little ugly because if I look at y, which is I want eventually this to match to, this is 1-dimensional and this is 2-dimensional. And so one of the dimensions has 1, right? If I look at the shape of this, it's 4 by 1. And what you can do is that if you have this extra dimension 1, which you may not require, you can call the squeeze function like this. What this will do is it will automatically remove this dimension because it doesn't actually add anything. And so here it will just take those 4 values. So here's the 4 values like this. If I don't call squeeze, it's like this. So it just removes that extra dimension that you may not require for that particular application. So now this is the same shape as y here, but you can see that the values don't really match up at all. And so what we're going to do is we're going to train our network. We're going to modify the weights of this matrix and this matrix so that this and this look as similar as possible. So the weights of the matrices M1 and M2, they constitute the weights A of the network defined above. So in order to optimize for these weights, we're going to use a little bit of object-oriented programming. This is the way it's typically done in PyTorch. When you construct a network, you would use a class. And so here we're using nn.module as a superclass. So nn.module is sort of like a base thing that you use. You would call it as a superclass because there's lots of functionality that this class can interact in. But as the user, you only need to define a few important things about this class for yourself. So the first thing I'll do is I'll define the init function. That's for creating the class. I initialize the super function, which is nn.module. So everything about nn.module becomes initialized. Then I define my two matrices, M1 and M2, the same way I did above, self.matrix1 and self.matrix2. So these become attributes of the class myNeuralNet. Then the only thing that you need to define, this is beautiful about this object-oriented way, is the forward function. So it says when I call this neural network on some data x, what's done to x and how is it output? So it takes in x, that's the forward function. It applies the first matrix, so x equals self.matrix1 x, so x gets modified. This is sort of bad notation, but it's probably the best way of doing it here. So x gets modified to this, then it gets modified again by the second matrix. That's sort of what I'm doing here. And then I call x.squeeze. I did that up here as well so that it returns a 1D array. So I have my neural network. So constructing the neural network in this object-oriented way, using the subclass of nn.module, it allows the parameters of the network to be conveniently stored. Because here, like, it will keep track of all these parameters here because I've subclassed this here, and I can show you that. So here I create an instance f of my neural network. So this is the network, and I can, sort of pass in x to this, and it will return a result. So it's a simple way of containing all the information of the network in a single class. But more so, when I talk about the parameters, there's a method in this class called f.parameters, and I can loop through all the parameters of this network and print them like this. And so, for example, here's my 2x8 array. That's sort of the first matrix that I've defined here. And then it also contains my 1x8 array. So it contains all the parameters nice and neat here. And what's going to be done is we're going to optimize those parameters, and everything works in sort of an object-oriented way. So everything will work with this class quite nicely. So like I did above, I can pass in data to the network and I get my prediction y hat. And I can compare that to y, and as you see, they're not very similar. So we need to adjust the weights, the parameters of these matrices so that y and y hat become as close as possible. So adjusting a, the parameters, so that y hat and y are similar. So for this, we need the loss function. The loss function is going to dictate how we adjust a so that y and y hat are similar. Remember, the loss function is sort of what I defined here. It could be the mean squared error between the predictions and the true values. So here I define LL. This is the mean squared error like I defined above. So nn.mse loss is just a function, and it's a function that takes in two things, y and y hat, and returns the corresponding mean squared error. And what that's actually doing is it's taking the mean value of y minus y hat squared. You see it returns the same value here. So this is just the mean squared error, but this is sort of the way that you would define loss functions. It's just convenient to do this way in PyTorch. It comes pre-packaged. So if you note that the loss function L depends on A, and the reason why the loss function depends on A, you might think, well, no, it doesn't. It depends on y and y hat. Well, y hat, the predictions depend on A, because if I change A, then the model is going to give me different outputs y hat. And so for this, analysis, which we'll be doing, it's useful to think about the loss function as a function of the parameters. And as I change the parameters of the model, the predictions will be different, but what's most important is that the loss function will be different. And the loss function, if I change the knobs, all the different parameters A properly, the loss function should get smaller. And so now we get to the main idea behind machine learning. And we'll go through slow to sort of understand this. The main idea is we're going to compute the gradient, dl dai. So there's a lot of different parameters in A. In our case, it's 24 parameters. We can compute the derivative with respect to each one of those parameters for each parameter AI of the network. Remember, there's 24 parameters in our network. With machine learning, okay, so we have the gradient. And remember that Torch keeps track of gradients if you've seen my previous video. Then what you do is you adjust every parameter like this. AI goes to what it was minus L times this gradient here. So what you do is you take each of those parameters and you adjust them ever so slightly. And you might think, well, why are we doing this? What exactly is this going to do? And L is the learning rate. So L is just a constant. L could be 1, it could be 2. Usually it's like 0.01 or 0.001. It's a small value so that these get adjusted ever so slightly. And when you first see this, you think, well, what the heck is going on here? Why is this making our predictions better? Well, let's look at a loss function that only depends on one parameter. So there's only one AI. And here's my beautiful drawing, which I drew in Paint. It's, copyright, don't sell it. It's beautiful work of art. But here I have the loss function on the y-axis and my single parameter A on this axis. And remember, the idea is that you want to change all the A's so that the loss function, which I plot in blue here, is as small as possible. So remember, all the A's are initially randomized. The weights of those matrices were randomized. So suppose I'm starting here at this point on the curve and I evaluate dLdA and it sort of looks like this. Well, I want to move along this curve so that I get to the place where it's as small as possible. And if I know where I'm at and I know the slope, if I follow that slope, I should be moving to a point where, L gets minimized. If there's only one global minimum, that's sort of the case. If L is bumpy like this, well, you can get stuck in local minima, especially for the case in one dimension. It turns out this doesn't happen quite as often, or it's not quite as bad in, millions and millions of dimensions, which if you have millions of parameters, you're million dimensions. But here I have one parameter. So I know the slope and I know the value I'm at. And if I follow that slope, move downwards, I should get to this place where it's 0. And so if I go AI, so here's my A value here, minus L times dLdA. So dLdA is positive here. And so I go AI minus some like 0.01 times a positive value. So AI is becoming negative. So I move to the left, right? And so I'm moving down the loss function. But if I'm here and dLdA is negative, then AI goes to AI minus L times a negative value. So AI gets plus a little small value here. So here AI moves to the right. So depending on what the slope is, I change A in the direction that makes the loss function smaller. And I want the loss function to be as small as possible. That's how my model does the best as possible. So that's what I'm doing here when I adjust every parameter. And I do that for all the parameters of my neural network. So you do it once, then you do it again, then you do it again, and over and over and over and over and over again until you reach sort of the minimum of your function. This general procedure is called gradient descent. And so each time you pass through the full data set X, and I'll sort of describe what this means, because we're doing this obviously here, it's called an epoch. So an epoch is a full pass of your data set. So in our case above, if you're looking at this or, this, the loss function can be evaluated at your entire data set, right? So think about how I defined L here. I'm summing through all the different i's in my data set. But sometimes your data set is really, really, really big and your loss function is complicated and you can't evaluate this efficiently on your whole data set. Maybe you don't have enough memory on your computer, for example. Well, in that case, you might only use part of your data set. And so you do this for part of your data set, then you do this for another part of your data set, and you sort of go through the entire data set as you do this. And so in that case, you might do this 5 times to get through, if you split your data set into fifths, you go through this 5 times. Each time this is evaluated using a slightly different part of your data set. But every time you go through the whole data set, it's called an epoch. So here I use the SGD function. It means stochastic gradient descent. A little more complicated than gradient descent, but again, I don't want to get into that quite yet in this video. But what it does is it takes in all the model parameters A, because this is the thing that it's going to have to adjust. That's what's being adjusted here. And it also takes in the learning rate L. So here I say my optimizer is SGD, takes in all the parameters I want to change, and it takes in the learning rate. So now I have my optimizer. And what I define here is basically the adjustment of the parameters over and over. So here I'm going to store my loss function after each epoch. You'll see the loss gets smaller and smaller and smaller. Y and Y hat get closer and closer together each time I adjust the A's ever so slightly. And so I'm going to adjust the A's 50 times. So the first thing I do is I call opt.zeroGrad. This will make sure that the gradient doesn't get built up over time in PyTorch. It will automatically set it equal to 0, so it only accumulates from a certain point. I call my loss function, so this is L of f of x. F of x is the prediction. Remember, f is my model, x is the data. So here's my model prediction, and here's the model value here, y, and I compute the loss value like this. Then I compute the gradient. Remember, dl dai is this thing here. I need it for computing the optimizer. So I compute the gradient. Then I do opt.step. That will adjust all the parameters like this. This is how it's sort of written in PyTorch. And then I'm going to append the loss value to this list. So now I have the losses each time that I adjust the parameters of my model. Then I'm going to plot the loss function as a function of iterations. So it starts off really bad and it gets smaller and smaller and smaller and smaller. So I'm adjusting all 24 parameters of those matrices of my neural network to make y and y hat as close as possible. So in summary, remember, my x's look like this. So 6, 2 to 1, 5, 2 to 5, 1, 3 to 2. It's coming up with a matrix, complicated sort of matrix operator or sequence of matrices that gets me from 6, 2 to 1, 5, 2 to 5, 1, 3 to 2, and whatever. It's going to be as close as possible. So it's not going to predict quite 1, quite 5, but it's going to be close. And I'll show you that here. So here's the output of my model after optimizing. And here's the values that I want. And remember that this is a curve fit, so they're not going to be exact. And in fact, it was pretty strict, the constraints I give. It's 2 matrix multiplications, all these slightly different values to get as close as possible. And so it turns out that the closest it can possibly get is, well, 3.62 is not very close to 1, 3 not very close to 5, 0.7 to 2, and then 4.49 and 5. So what it's saying is that as I optimize my model, I'm never, with a simple model that I've defined, 2 matrix operations, this is about as close as I can get for the pattern of getting, the pairs of numbers to the corresponding 1, 5, 2, and 5. In later videos, we'll get more into networks. We'll define more complicated networks to do more exciting and complicated things. But I hope you enjoyed this video. If you did, be sure to like and subscribe. There's going to be more machine learning tutorials in the future, and I'll see you next time.